Now we are into the fifth unit of our subject, natural language processing. So, in the first unit, we have seen about the words and documents, and we have seen what is morphological analysis or morphological parsing. In the second unit and third unit, middle, we have seen what is syntactical parsing and what are the various methods used for syntactical parsing. Then, in the third unit, second half, and the fourth unit, we have seen what is semantic parsing, what are the methods used for semantic role labeling, what is word sense disambiguation, what is predicate argument structure, what are the different systems and resources and softwares used in each case. Then finally, we have come to the last unit of this subject, and the title of this is language modeling. So let us dive into this fifth unit. So we'll be start with what is language model. We are talking about LLMs in the days uh, and ChatGPT, Google, Gemini, and Perplexity. All these are language based on language models. So, language model is used to understand the structure and flow of natural language. And language modeling assists us in predicting and generating or correcting language sequences. So, as we have been seeing, that whole NLP applications can be summarized as speech recognition, machine translation, text prediction, auto-completion, grammar correction, chatbots, dialogue systems. All these are based on the language models. So, how the language modeling is done is the probability that we'll be calculating for each sentence. For example, there is a word W1, then W2, so on, Wn. These probabilities are calculated using a chain rule with the product of given all other I minus 1 words, what is the probability of that word Wi? So this is the chain rule, but it is computationally expensive. So we know the Markov assumption. What is Markov assumption? The present state depends only on the previous state, not on the other things. That means the ith state depends only on I minus 1th state, not on I minus 2, not on I minus 3, I minus 4, and so on. So here also, the probability of Wi depends on I minus 1 only, not the remaining ones. So this is the Markov assumption that we'll be using. So language models are two categories. One is statistical model, that's we are going to study shortly. And in the statistical models, we are going to see n-gram model, combinations of words, unigram, one word, bigram, two word, trigram, three words. Then we are going to see what are the smoothing techniques, and especially we are going to study back of smoothing technique, linear collation smoothing technique, nez or nay smoothing techniques. And second category is neural language models, which are feed forward neural networks, recurrent neural networks, RNN, long short-term memory, GRUs, and transformers, which are BERT and GPT. These are neural language models. So, in language modeling, given the present sentence, even in WhatsApp or Google, when you type certain words, automatically it will suggest next word by predicting it. So, this is done using language modeling. For example, I love. I typed I love. Next, the model will predict what will be the next. So suppose I am studying about NLP, the next probable word is I love NLP. And suppose if it is trained on food blogs or about food, the next predictable word is pizza, or otherwise rain which is low probable. Probability of rain will be less. So a good language model will assign higher probabilities to semantically and contextually appropriate words. Here NLP and pizza will have high probability, rain will have low probability. This is how it will be predicted. And how the language models are evaluated. One, there are two parameters to see the evaluation of language model. One is perplexity. Perplexity is the ambiguity. The lower the perplexity, higher the performance. So we'll see about that very shortly. So I'm not going into deep into this. So remember one point, lower the perplexity, higher the performance. And it will be calculated just we have done with decision tree entropy. And other parameters are also there for translation view, accuracy for classification, for summarization row. These are the different parameters. So obviously we have seen already what are the applications of language modeling. So we'll start with n-gram models. So n-gram model is a type of probabilistic language model that predicts the likelihood of a word based on the previous n minus words. So by Markov assumption, what is the Markov assumption? The probability of a word depends only on fixed number of preceding words, not all the words. So the probability of a sentence or word sequence W in natural language, we cannot calculate directly because every natural language has a rich set of words, and calculating the probability of particular sequence is very, very typical. So this is the general chain rule of probability, accounting from word 1 to word t minus 1, and those product of all those probabilities. By Markov assumption, we are considering only up to t minus 1 words starting from t minus n minus 1. So this is Markov assumption. And what is n-gram model? Suppose you are considering a single word, solo word, we call that unigram. Suppose we are considering the present word and the previous word, then we say that it is bigram model. Suppose I am considering previous two words, it is known as trigram model. So if it is n-gram model, this is the nth word and these are the previous words. So the n-gram model is a Markov model of order n minus 1. It will consider n minus 1 previous, present word, nth word, previous n minus 1 words. So as we have already seen in the introduction, how do we evaluate a language model? So there are two factors to evaluate language models. One is coverage rate, another is perplexity. Coverage rate is the proportion of n-grams in the test set that was already covered in the training data. That means if you have the test data sequence in the training data, means it has a better coverage and it can perform well. Suppose in the test data is not covered in the training data, then we say that it is out of vocabulary term. If the model encounters a word or sequence that was not in the training data, it is considered as out of vocabulary item, OOV. So OOV rate is the percentage of word types in the test set that were not observed during the training. So the lower out of vocabulary means better coverage. So this is one parameter, how much it covers. Second parameter is perplexity. Perplexity is measured to evaluate how well a probabilistic model will predict a sample word, how well it is predict, how well it predicts the next word. So in the it perplexity measure, it tells us how confused it is. That means lower the perplexity, better the performance. Perplexity is Brahma, Branti, that is more appropriate word. So that means higher the perplexity, less the clarity. Lower the perplexity, more the clarity and performance. So we calculate it in terms of just now, just as we have done in entropy. If you remember in decision tree algorithm, we calculated the entropy using sigma minus sigma pi log pi. That was the formula we used. For example, if you have 100 samples, 50 are saying yes, 50 are saying no, then the entropy is 1. And that means no decision can be taken from the given data. Data is there, but it is not giving the data. That is the entropy. Similarly, perplexity is the confusion. How much confusion is there? So we calculate it based on the 2 to the power of HQ. HQ is the entropy of the distribution, which measures the uncertainty. Just as I told you, if you have 100 samples, 50 are yes and 50 are no, then it is uncertain. There is nothing you can infer from that data. Suppose 80% saying no and 20% saying yes, I can take a decision that no is better option for me. So entropy tells us uncertainty. So perplexity is a measure of entropy. And generally, entropy is calculated from the formula e to the power of minus 1 by t sigma log q of wi, where q of w is the probability assigned by the model to a word wi. So wi is the ith word, t is the total number of words in the test set. So this uh, formula is used to calculate the probability, perplexity. Higher the perplexity, lower the performance. Lower the perplexity, higher the performance. So perplexity can be seen as the average number of choices the model is considering at each word. If the perplexity is 10, that means the model is unsure, as we have to choose from 10 different likely words. Lower the perplexity, lower the options, more the certainty. Higher the options, less certainty. So perplexity is useful when the task is to predict next word in a sequence. For example, in speech recognition or machine translation, the model should not only predict but also distinguish between what are the correct sequence and what are the incorrect word sequences. So perplexity is necessary, but it is not sufficient. We will be seeing other parameters also. The next topic in the language model, what we have seen till now, what is language modeling and how it is done. Actually, it has to be done with probability chain rule, but it is computationally expensive. So we adopted Markov assumption that the present nth word depends on only a set of n minus 1 words. Then we have seen how to evaluate a language model. Two factors we have seen. One is coverage, another is perplexity. Coverage is the percentage, the fraction of the test sequences already seen in the training data. So if that is not there, we call it as out of vocabulary set. Then second one is perplexity, uncertainty, or number of more options. So lower the perplexity, higher the performance. Going further with language modeling, we will see likelihood and smoothing, maximum likelihood. If you remember machine learning subject, in the Bayesian equation, we talked about likelihood. So maximum likelihood estimation is a statistical method for estimating the parameters of a probability distribution. This likelihood, it chooses parameter values that maximizes the likelihood of the observed data. So in other terms, it is the probability values that makes the observed data most likely. Suppose we have given data, how likely that data is to be true. Suppose you were doing a cancer test, how likely that, what will the base probability given the test is positive, what is the probability that a person will have cancer? That is the probability you are going to calculate. What is the likelihood there? What is the likelihood that a person having a cancer will get a test result as positive? That is the likelihood. So to understand this concept, let us see, suppose you have a coin and you are tossing it for 10 times, and the sequence is head, tails, head, tail, head, tails. Totally 6 heads, tails 4. And what is the probability of likelihood of head is 0.6, and the probability of tails is 0.4. So based on this data, it is likely that the coin is slightly biased towards heads. That is a likelihood. For example, in language modeling, suppose I have a sentence, I love, that is a bigram, 2 words, and the count is 100, frequency is 100. And the count of I love life is 30. Then what is the likelihood that given I love life, the probability of occurrence of life given already I love is there is 30 out of 100 calculated from the count of the trigram by the count of bigram. So whenever I love comes, it is likely that 30% of the time the life will come. That's how the likelihood informs me. So it is very, very important estimation in statistical modeling. Now in language modeling, we'll be calculating this MLE. For example, you are talking about trigram. Trigram means you are considering the present word, previous word, previous 2 words. So the probability that previous 2 words occurred already, given that these 2 words occur, what is the probability that it will follow? Then the count of frequency of trigram by frequency of bigram. This is the likelihood. So another example, trigram is he is tall, that is occurring 15 times, whereas bigram he is 100 times. Then the likelihood that given he and is, the likelihood of occurrence of tall is 15%, 15 by 100, 50%. But there is one problem with this likelihood estimation. For example, suppose I have a trigram. He is fair. He is fair. Is it wrong? No, it is correct. It can happen. But unfortunately, I don't have that trigram in my training data. So what will be the probability? 0. So the probability of fair after he is 0. Because it is not present in the training data, I cannot proceed with 0 probability. I need to assign some minimal probability even if that trigram is not in the training data. That assignment of non-zero probabilities is known as smoothing. So if a word sequence never occurred in training data, then our model, our likelihood estimation would be 0. This is problematic because It is valid. He is playing. He is fair. So not because it is not occurring in the training data, it is occurring only 0 times, then zero probability, that will be a problem. So we need to assign at least some minimal data. That is known as smoothing. So what is smoothing in the language model? Smoothing modifies the maximum likelihood estimation to avoid zero probabilities. And it gives small minimal probability to the unseen n-grams and reduce the probability of very, suppose one n-gram is occurring very frequently, but that doesn't mean that it has high probability. It has to be normalized. So smoothing will help us in generalizing beyond the training data, because our training data may be biased. So one thing which are not occurring should not be given 0 but should be given some value. Which are very frequently occurring, they should be normalization. So there are many techniques for smoothing. We are going to see two techniques in our class. One is known as back of smoothing, another is known as Ney-Nazar smoothing. So back of smoothing.